welcome to the third and last session of the colloquium. Today is my real pleasure to introduce Professor Tuncay Aktosun, my long-time well, it's a pleasure to introduce Professor Tuncay Aktosun, my long-time collaborator. We share many mathematical adventures together, right? Professor Aktosun graduated in 1986, so his PhD in Indiana University at Bloomington. His advisor was Roger Newton, who was one of the main researchers in inverse problems, right? And well, since 2005, he is a professor at the University of Texas at Arlington. He worked in inverse problem, scattering, wave propagation, integrable nonlinear equations, application to physics, material science, biological science, and geophysics. He's actually one of the leading experts in his area of research. And also he has a large experience in introducing undergraduate students to research, right? I am sure you will realize that on his talk. So today he will talk about finding the shape of a human vocal tract from speech sound. So, Professor Aktosun.
Muchas gracias, Ricardo. Well, it's my pleasure to be here. I've been visiting IMAS for many years now. And, the negative thing is that the people in Mexico are so nice, and I can communicate with them. So when I'm in another country, I'm forced to speak their language because they refuse to communicate with me. But in Mexico, people are so nice that I can communicate with them even without using any language. And unfortunately, that made me very lazy. So I only know basic expressions in Spanish, but we will communicate in English. Well, first I prepared a very mathematical talk, but then I noticed that there are a lot of future scientists, future mathematicians here. So I try to make my talk less mathematical because who knows, maybe the mathematics that I use is not the best one, but I'm hoping that I will be able to excite some of you so that you can come up with the better mathematics, newer mathematics, and more improved mathematics. So I will tell you about how the human speech is produced and how we can use this to our advantage. So the title of my talk is Finding the Shape of a Human Vocal Tract from Speech Sounds. Well, I must admit that I hated biology and I refused to learn all these names because in mathematics, well, maybe we like mathematics because by learning so few things, we can do so much. So I will be introducing some terminology, but well, it's okay if you don't remember it, but I'm hoping that I will be able to excite some of you so that you can just work in this field. Oh. Well, here's the outline of my talk. Recently I published a paper with a collaborator, and since this talk is based on that paper, I will just mention that reference. And then I will tell you how human speech or speech sounds are produced. Well, the main ingredient is the vocal tract, so I will tell you about the vocal tract. And then I will tell you that, so there are essentially two theories. One is called the spectral theory. So this deals with the discrete frequencies, and the other is the scattering theory. So there are very few discrete frequencies in the scattering theory, but there is the variables will be a continuous variable. So I will just tell you about this. In fact, most people in this field, when they analyze the vocal tract, they use the spectral theory, even though some scattering theory is used. But I will mention the spectral theory, but I will also mention the scattering theory, where my interest lies in. Well, as you know, there is the famous area of mathematics or mathematical physics now known as quantum mechanics. Well, from the physics viewpoint, quantum mechanics is the analysis of atoms and molecules, etc. But from a mathematical viewpoint, quantum mechanics, in some sense, was developed as functional analysis, as an infinite-dimensional linear algebra, a combination of differential equations, analysis, and linear algebra, but not in a finite-dimensional setting, but in an infinite-dimensional setting. So there is this well-known equation or operator known as the Schrödinger equation, or the Schrödinger operator, and in some sense it forms the basis for understanding many other problems. And well, it turns out that in this case you can convert the problem into a problem to analyze the Schrödinger equation. So I will mention that, and then I will mention the relevant, the so-called direct problem and the inverse problem. So the direct problem in this case will be, well, the vocal tract will be responsible for producing the sounds. So if I know the shape of the vocal tract, can I produce the appropriate sounds? And the inverse problem is, well, if I know, for example, if I hear the sounds, can I just produce for you the shape of the vocal tract? So let's continue. So here's the relevant reference. Well, this is joint work with my collaborator, Professor Paul Zaks from Iowa State University. Well, I must mention that because of my training, I know I do mathematics more in the frequency domain, so I talk about analyticity, etc. Well, my collaborator, Paul Zaks, he lives in the time domain. So he talks about causality, I talk about analyticity. And, but it's good that when we get together, so we somehow complement each other. So it's so nice to collaborate with others, and I'm sure when you graduate, when you become graduate students or faculty members, you will travel all over the world and make so many collaborators. So it's very enjoyable to collaborate. So, I'm interested in sounds related to a language. Well, there are certainly sounds that we produce. Well, for example, I thought I never snored when I slept because I'm single and I always just stay in the room by myself. But one day, I guess one of my friends came, and even though he was staying in the other room, but he said, well, you're snoring. So, well, the snoring, so you're not going to be dealing with snoring. Or so sometimes, for example, if you eat too much, well, you belch. So we're not interested in those sounds. So we're only interested in sounds of language. Well, it turns out that, well, in the world, there are over 5,000 languages. And the linguists or other scientists go to Africa, Latin America, so to many parts of the world, and they try to record these record the sounds in all these languages. But so far, I guess only 500 languages have been analyzed. And so sometimes some languages are disappearing, but the scientists just try to record these languages, and they try to understand these sounds. Well, now, how do we produce the sounds of languages? So let me see if I can show you. So what happens, so this is called the vocal tract. Basically, it's your throat, and here you have the lips or the mouth, and this is your tongue. And so this part, this part is called the larynx. I hope you don't smoke, because some of the smokers get cancer right here. So please don't smoke. So, in the middle of the larynx, it's about, I guess, maybe 3 or 5 centimeters in height. So you have the vocal cords, or I guess in British English they're called vocal folds. Essentially they are lips. What happens is that so to produce sound, you inhale. So you swallow air, and the air goes. But right here, there are 2 passages. So one goes to your stomach. If it's food, it will go to your stomach. If it's air, it will go to your lungs. So the air goes in your, through the larynx. It goes through a pipe, and that pipe is called either the windpipe or trachea. And then, it separates into 2 pieces because you have 2 lungs, and the air goes into the lungs, and the lungs just blow up, and then they just send the air very fast back, and it goes through your trachea, and then it goes through the vocal folds or vocal cords. Somehow to produce sound, just imagine that you have a balloon, and the mouth of the balloon has to be very small, because if it's very big, there's not going to be any pressure, enough pressure to produce the sound. So the vocal cords will vibrate, and in fact, I'll show you in a second. And then, so those vibrations cause the air sitting in the vocal tract here to vibrate. They vibrate, so the air molecules vibrate in a longitudinal way, and that causes the sound to be produced right in the vocal tract here. And meanwhile, your tongue and the so-called articulators, so they are just adjusting themselves, and then the speech sound just comes out, and it is radiated here. And it goes either to a microphone or to the listener's ear. So let's look at that. Your vocal tract is essentially, it's a tube. Just imagine that you have all these tubular instruments, and it should be somehow very narrow here, and it should be not too wide, but it should be wide enough here. So basically, this is your vocal tract. And just imagine that when you have a musical instrument, you blow here, and then the sound comes out here. Well, the length of the vocal tract, I guess for adults, it can be about 20 centimeters. Maybe for children, it's shorter. So between 6 to 22 centimeters long. So when you produce sound, basically there are three elements. So the lungs, well, they absorb this, the air, and while doing that, the lungs are larger, and then they send that air at high pressure through the vocal cords. The area between the vocal cords is called the glottis. And then, because the glottis is really small, that area is small, so high pressure waves are created here, and then everything takes place, the speech production takes place in the vocal tract, and it just goes out of your mouth. So, well, these are the vocal cords. You see, there are two lips, and basically they vibrate as the air coming from the lungs as it goes through the vocal tract. Well, I guess we don't need to. Okay, so now let's look at
Inhaled air and ingested nutrients both pass through the oropharynx behind the oral cavity. A cartilaginous structure called the epiglottis directs food and fluid away from the trachea and into the esophagus, preventing inhalation of this material. The stem of the epiglottis attaches to the hyoid bone and the anterior rim of the thyroid cartilage. The superior portion of the epiglottis moves freely and can swing up or down like a trapdoor. With each swallow, the larynx rises and the epiglottis folds down over the laryngeal opening, closing off the airway. If particles make their way into the trachea, the cough reflex pushes air forcefully up through the larynx, forcing the particles back up and out.
Well, so perhaps I can just, since my biology knowledge or anatomy knowledge is very minimal, so perhaps I can just state this in plain English. So basically, I never had anything to do with religion, and well, sometimes people ask me, oh, don't you think there is God? Well, I said, I don't know. But it's amazing that, so when, I guess human beings are created, they were created in a very efficient way. So what happens is that we use our mouth both to, inhale, both for, to get the air, and also we share our mouth to eat. So what happens is that, somehow, the air and the food share our throat. And then right here, somehow we know whether it is the food. If it is the food, then it needs to go to the stomach. If it's the air, it needs to go to the lungs. And there is something called epiglottis. Essentially, there is that wall, and somehow that adjusts. If it is the food, then it goes into the stomach. Otherwise, the air will go to the lungs. And by mistake, well, for example, if you're in a hurry, if you eat too fast, well, some of the food may try to go to your lungs, but then you cough, and well, the food is pushed back, and then it goes in the right direction. So let's see if we can see this once more.
Inhaled air and ingested nutrients both pass through the oropharynx behind the oral cavity. A cartilaginous structure called the epiglottis directs food and fluid away from the trachea and into the esophagus, preventing inhalation of this material. The stem of the epiglottis attaches to the hyoid bone and the anterior rim of the thyroid cartilage. The superior portion of the epiglottis moves freely and can swing up or down like a trapdoor. With each swallow, the larynx rises and the epiglottis folds down over the laryngeal opening, closing off the airway. If particles make their way into the trachea, the cough reflex pushes air forcefully up through the larynx, forcing the particles back up and out.
Okay, I guess we can get rid of this now. So let's look at the next slide. So, in languages, so there are speech units, and they are called phonemes. Well, for example, in English, when you say book, well, there are 3 phonemes. So each one of these phonemes lasts about 100 milliseconds. Well, this is like watching an animation or watching a movie. So, well, when you have the movie or the animation, well, you have these static cells. And each one lasts about, well, there are about 12 cells per second, 12 frames. And, well, you see each cell by about 1 over 12 seconds. But then it is as if you see the motion picture. You see the movie as if, well, the objects are moving. Well, in some sense, the same thing happens when you speak. Well, at least mathematically, you can describe it that way. So what happens is that when I utter the word book, well, for about 100 milliseconds, I utter the consonant, and then for the next about 100 milliseconds, I utter this sound, this phoneme. Well, it's called a vowel. I say, ooh. And then for the next 100 milliseconds, I say, k. But since I say this in some continuous way, you hear the word book. Well, it turns out that all these sounds somehow are given names and symbols, and, well, there's the so-called International Phonetic Alphabet. Well, they classify essentially these sounds as either vowels or consonants. Well, there are about 107 letters in the International Phonetic Alphabet, and I guess this is all started, well, some French and German teachers got together around 1886, and they said, well, let's just try to have some universal symbols for all these sounds in different languages. So they mainly use the Latin characters to assign some symbols for each sound. But then it turned out that things were very complicated. And since they were not mathematicians, well, I think it's a mess. And occasionally they get together. So there is the International Phonetic Association. They get rid of some sounds because perhaps the languages are disappearing, and then they add new symbols. But not everybody somehow agrees with that. Well, for example, in the United States, they change the symbols a little bit. And depending on your goal, well, they may be using different symbols. So basically, we have vowels and consonants. And so let me just show you.
Whether you are an English learner, an actor, or someone generally interested in linguistics, learning the IPA, the International Phonetic Alphabet, is going to greatly benefit you. Hello and welcome to another lesson here on English Like a Native with me, Anna English. Now, if you are specifically interested in accents, I have many videos here that can help you, and they will be listed in the description box below. If you are an English learner, then you are in luck because there are hundreds and hundreds of English lessons here, especially for you, with many more being released every single week. So make sure you press that subscribe button and the bell notification button so you don't miss out on future lessons. So, the International Phonetic Alphabet. The phonetic alphabet is literally just a way of writing down sounds. So if you want to know how to pronounce any word, once you know phonetics, then you can look up that word in the dictionary, and normally next to each word there will be the phonetic spelling. That means you can see exactly how that word is supposed to be pronounced. And that's why it's so helpful. So what are we waiting for? Let's get started.
So first, the consonants.
Like peanut, pencil, please, big, bad, baby, take, two, turtles, donuts, don't, disagree.
I hope you got the idea about the consonants. So let's see.
Dancing.
So then she'll talk about the vowels.
Lake, love, blue, yellow, what, why, when, me, see, we, happy, very, wary, sit, hit.
So, well, I will stop here. So why is this a big deal? Well, this is very useful, for example, for singers. So opera singers, for example, are supposed to be producing, say, 5,000 sounds, or they sing in different languages. So they learn about the International Phonetic Alphabet. Or actors, for example. Well, when they act, they have to, for example, even a British actor, when he or she plays in an American movie, well, you cannot tell the accent, for example. So, for example, the speech therapists, so they need to train the people so that those people can speak properly. Now, what is a vowel and what is a consonant?
So let's actually talk about what is involved in what goes on in your mouth. How do you make a consonant? What is a consonant? Well, a consonant is an obstruction of air. It's basically you're getting in the way of air coming out of your mouth, and that makes some sort of sound. There are sort of three components of every consonant. One of them is called voicing. It's basically, are your vocal cords doing anything? And so you get this...
Well, I'll stop here. So the consonant is nothing but somehow a barrier to the sound, he said. In fact, let's just check. Well, I guess I can skip this. So this is the shape of the vocal tract when you utter vowels. Well, again, the vowels, so please look at the shape of the vocal tract. No matter what that vowel is produced, so there is no obstruction here. But let's see what happens when we have but let me just move this. So here, these are all the vowels, and when you produce the vowels, look at the shape of the vocal tract. So it's a constant shape for each vowel. But let's see what happens when you utter a sentence. Now you have both vowels and so this is, I think, English. So this is the MRI imaging while speaking. So now let's take a look at, for example, let's look at this animation when you say Ohio. Well, let's see what happens when there is some consonants. So here it says the brown cow. So let's watch it again. See, in some places the vocal tract, so the top and the bottom just get together. So there's an obstacle. So that's when you have the, during a vowel production, the vocal tract shape, so the vocal tract is open essentially, but when you have a consonant, then there's obstruction is created because the two edges, essentially the vocal tract cross-sectional area becomes zero at some points. Well, here it says, he had a rabbit. So notice that when you pronounce the consonants, the vocal tract area at some points will be 0. So I hope I was able to convince you that the sound is produced in the vocal tract. So what is now the mathematical part? Well, the vocal tract is, well, in some sense, like a cylinder. And for mathematical simplicity, you can just assume that it is closed at this end and it is open at the mouth. Well, this is a uniform cylinder. So how do you produce sound? Well, basically, you just need to excite this. So whenever you have some system, you excite the system by sending some waves, and that system happens to have some resonant frequencies. So you can, if you excite the system at one of those resonant frequencies, the system will vibrate violently. So basically, from this end, you excite the system, and if the system is uniform, so if this end is closed, if this end is open, so I hope well, either you've studied this in a physics class, or well, you can just essentially guess what happens. So this is the length of the vocal tract, the uniform vocal tract, and when you produce a wave, and the wave here, so there should be no vibrations here, and so the vibrations here should be free. Basically, to this length, you can fit 1/4 of the wavelength. And then you can fit 3/4 of the wavelength. So it goes like this. And then you can fit also 5/4 of the wavelength. So as a result, what happens is that if this is your vocal tract, then you can produce an infinite number of frequencies, and those are known as the resonant frequencies. And well, those resonant frequencies are known as formants. And well, they're usually named as F1, F2, F3, F4, etc. But it's amazing that those linguists can essentially get away with murder. Namely, they use only the first 2 resonant frequencies, and perhaps 3, to identify all the sounds. Whereas in mathematics, well, you have infinitely many of them. So basically what happens is that since the vocal tract does not have a uniform cross-sectional area, so when you utter, for example, a vowel, so you have all these different frequencies, and the formants are these frequencies where the peaks occur. So here, whatever this frequency is, that's F1, and here at this frequency you have F2, at this frequency you have F3, and here you have F1 and F2, and for each sound produced, for each phoneme produced, you have a particular shape of the vocal tract. And that shape essentially depends on the person. So that's, well, thanks to that, we're able to identify. Well, otherwise, well, we would not be able to recognize. For example, well, the blind people, for example, can identify each other from their voices. Or, for example, you can use this to your advantage. So instead of just typing your password, especially these days, well, in our university, they ask us to change the password every so often, and so long passwords. But how nice it would be, you go to your computer, well, you utter something, and then, well, so your sound is converted to the shape of your vocal tract when you produce that sound. Because that sound is unique, the computer recognizes you, and without typing your password, well, you log on. Now, remember, this sound, the continuous sound is produced by having all these phonemes come in successions. So let me just show you the following.
Okay, this is the control device for Gunnar Fant's classical UV1 speech synthesizer from 1953. What I want to show you is what we have done to bring this brilliant interface into the 21st century using motion capture techniques. So by moving this stick in 3 dimensions, I can control first and second formant and the fundamental frequency. This is too hard. Let's hand it over to the expert.
Ja, jag heter Gunnar Fant. Jag är professor emeritus. Det vi ser här är vår första talmaskin som hade ett inventarium med enbart vokaler och vokalliknande ljud. Jag kan göra en rörelse på det här sättet. Och då blir det how are you? Och jag kan göra en annan rörelse. I love you.
So, well, I hope you were able to follow. Basically, what happens is that there is the vowel chart, and so they use some mechanism, and they excite each vowel for about 100 milliseconds, and then by going over different vowels, so first they create the sentence, I love you, and then how are you? Well, would you like to see it again? Well, perhaps we can look at the second part. By the way, Gunnar Fant was a well-known linguist.
This is too hard. Let's hand it over to the expert.
And this machine is from
Ja, jag heter
1953.
Gunnar Fant. Jag är professor emeritus. Det vi ser här är vår första talmaskin som hade ett inventarium med enbart vokaler och vokalliknande ljud. Jag kan göra en rörelse på det här sättet. Och då blir det how are you? Och jag kan göra en annan rörelse. I love you.
So now let's go back to mathematics. So, well, so when you so because sound is a wave, so you need to talk about the wavelength of the sound, and one over the wavelength is called the wave number. So how many waves you have, how many cycles you have in 1 centimeter. Well, you can also talk about the angular wave number. So remember, if you multiply something by 2 pi, then you can say it is measured in radians. So number of radians per centimeter, and that's usually denoted by K. And then you have the frequency measured in hertz, number of cycles per second, and if you multiply that by 2 pi, you have angular frequency, radians per second. And then you have, well, the speed of the wave is the product of the wavelength and the frequency. But you can also express that in terms of the angular frequency and also the angular wave number. And well, the humans can hear, the sound speed at room temperature, that's about 34,000 centimeters per second. And well, the air density, well, that's about 1.2 grams per centimeter cube times 10 to the minus third. And well, because it is the pressure wave, so there are two quantities, relevant quantities, the pressure and the volume velocity. In some sense, the volume velocity is you multiply the velocity by the volume. That's why the unit for the volume velocity is the velocity times the area. So you use these to describe the mathematical theory behind to produce sound waves. Now, here's the spectral theory. Well, basically, so you have these formants produced. So you have these resonant frequencies produced in the vocal tract. And they're usually denoted by F, F1, F2, F3, etc. And the vocal cords vibrate at frequency, well, it's called the pitch. Well, usually the pitch frequency is smaller, and this has nothing to do with the formants produced. Well, as I mentioned, the linguists usually use F1 and F2 only to identify the vowels. Now, when you have the vocal tract, well, you assume that in the inverse spectral theory, you assume that it is closed at one end, it is closed at the glottis. Remember, the glottis is the opening between the vocal cords, and it is open at the lips, at the mouth. And, well, as I mentioned, so you can use simple mathematics. If you have the uniform cylindrical vocal cord, then you have the length of the vocal cord. Well, you can fit in 1/4 of the wavelength, or 3/4, or 5/4, etc. You have infinitely many resonant frequencies. Now, well, you can convert that to frequencies. So you have these infinitely many frequencies, and they asymptotically they go like 2n times the speed of sound divided by 4L. Now, what happens if you have a non-uniform vocal cord? So during speech, well, physicists have this excellent idea. So you start with an unperturbed system, and then you perturb the system. So what happens is that these frequencies will be perturbed, will be changed a little bit. But you still have infinitely many of them. Now, well, as I mentioned, I do the scattering theory, even though I like the spectral theory, with no offense to Professor Weichard. So, well, in the scattering theory, you have these so-called acoustic equations. Basically, it involves the cross-sectional area of the vocal tract, and you have the pressure, and you have the x derivative of the pressure, and also the t derivative of the volume velocity. And here you have the air density, and also you have the speed of sound. So basically, by using these, you can describe the wave propagation, the sound wave propagation in the vocal tract. And so here x is the distance from the glottis, from the vocal cords, and L is where the lips are. So L is the length of the vocal tract. Well, as far as the sound propagation is concerned, even though the vocal tract is bent, but you can just assume that it is not bent. So the mathematics is unchanged if you straighten the vocal tract. And instead of talking about the vocal tract cross-sectional area, you can just assume that it's cylindrical. You can talk about the vocal tract radius. So, now, as I mentioned, I live in the frequency domain, so my training is, I'm more comfortable if I talk about the analyticity of a function rather than how things propagate in time. Well, you can do the so-called Fourier transform, Fourier integral, and but basically this says when you have a time signal, you can just decompose the time signal and it becomes an infinite number of frequencies. Well, if you do the inverse, but if you do the spectral theory, then here you're going to get the summation, and that's the Fourier transform, well, Fourier series. Here you have the Fourier integrals. Well, the same for the volume velocity. You have infinitely many frequencies here, and each has this amplitude. Well, you can rewrite the equation, the acoustic equations from, well, in the frequency domain, you essentially get this. Again, you have the vocal tract cross-sectional area as a function of x, the pressure and the volume velocity. Now prime shows the derivative. And, well, if you have two first-order equations, well, that's the same as one second-order equation. You can eliminate v, the volume velocity, and you get this equation, the second-order ordinary differential equation, and this is known as the Webster-Horn equation. Essentially, all how the sound is produced in tubular instruments can be described by this. Well, since this is second order, to solve it uniquely, to get that P of kx uniquely, you need two conditions. Well, so you can choose those two conditions as, well, here, for example, you can say, I want the volume velocity at the glottis to be 1, and I want this to happen. Well, basically, this is equivalent to saying, but it turns out that in almost all the languages, when you produce sound at the lips, at the mouth, the sound pressure wave goes out. Well, there are very few languages where the sound pressure comes in when you speak. So it is a reasonable assumption to make this assumption that the sound will go just out. So this mathematical assumption. Now, there are two problems. One is the direct problem, and the other is the inverse problem. So as far as my approach is concerned. So given the shape of the vocal tract, I'm interested in finding the sound pressure at the lips. And I can just measure that sound pressure by placing maybe a microphone here. And but in the inverse problem, I'm interested in just measuring the sound pressure by using a microphone, and I'm interested in determining the shape of the vocal tract. Well, mathematically, you can make it more challenging. Well, because this is complex, this is complex valued, maybe you can say, how about if I only measure the amplitude? So this is now going to be a positive quantity. Can you determine the shape of the vocal tract? Well, even though theoretically I need to measure this for all the frequencies, but in practice, since the human sound range is between 20 and 20,000 hertz, so I can measure K values roughly between 0.03 and 3. In fact, here's the conversion from K to F. Well, here's how you do the inverse spectral problem. So, well, Well, in the direct problem, given the shape of the vocal tract, you determine all those resonant frequencies. Well, in the inverse problem, knowing all those resonant frequencies, you're interested in finding the shape of the vocal tract. Well, there is in fact, this was mentioned in the previous talks. Well, a Swedish mathematician named Borg stated that, well, you cannot determine the potential in the Schrödinger equation, and that becomes equivalent to you cannot determine the shape of the vocal tract unless you have two sets of infinite frequencies. So, well, actually these two sets, they don't have to be frequencies. Well, for example, these may be the resonant frequencies, these may be some amplitudes, for example. But as I mentioned, I'm not going to analyze this as an inverse spectral problem. I'm interested in analyzing it as a scattering problem. So I make some assumptions, some mathematical assumptions on the vocal tract so that I will only be able to recover the vocal tract radii belonging to this group. But what I do is I just transfer everything to the Schrödinger equation. And then I forget about the vocal tract, and now I have the Schrödinger equation with the potential. Now, in the vocal tract problem, the x values go from 0 to L. Well, to do the scattering, well, I need infinity. So basically, I extend the vocal tract radius beyond the vocal tract length in such a way that the vocal tract radius will be continuous and the derivative will be continuous at the lips. So, and that's the same as saying the second derivative will be 0 for the vocal tract, so the potential will be 0. So now I have the Schrödinger equation with a compactly supported potential. So the potential is non-zero only between x equals 0 and L. And the connection also is that, so this is the Schrödinger equation, but with a non-Dirichlet boundary condition. Well, I must notice that when you do quantum mechanics, you always use the Dirichlet boundary condition. Well, it is because this wave function, when you do the separation of variables, from the three-dimensional case, when you go to the radial case, you divide this by r. So unless you make this 0 at x equals 0, because of that 1 over x term, well, you're going to get a singularity. But it turns out that in this problem, in the vocal tract problem, I have to use a non-Dirichlet boundary condition, and here's the connection. So this is the boundary parameter, and here I have the boundary parameter is related to the derivative of the radius, logarithmic derivative of the radius at the glottis. But then once I solve this mathematically, then I'm going to forget about the part of the vocal tract beyond, outside the lips, because it's meaningless. Well, in the language of Schrödinger equation now, I have a compactly supported potential, and there is the so-called regular solution satisfying these initial conditions, and there is the so-called Yost solution, and Professor Weikart also mentioned this, and there is the so-called Yost function, and the connection is, it happens that when I solve this equation, and when I get this solution, there's going to be a unique solution. That solution will be related, that solution evaluated at k equals 0 will essentially be the same as the vocal tract radius function. And the boundary condition will be the logarithmic derivative of the vocal tract radius function with a minus sign at the glottis. Well, so you can solve this direct problem, namely, if you know the vocal tract radius, then you can determine the pressure, and then well, this is the volume velocity, and you can also get, for example, the pressure at the lips. Okay, thank you. So I'll hurry. Well, mathematically speaking, the problem now becomes, so the original problem was knowing the pressure at the lips. I'm trying to determine the vocal tract radius. Now, mathematically now the problem becomes, if I know the so-called Yost function, then I'm trying to determine the potential and the boundary condition. And a more challenging problem is, how about if I only know the absolute value of the Yost function? Can I determine these? Well, there is a well-known theory by two Soviet mathematicians named Gelfand and Levitan, and so it is suited to solve this problem. And it turns out that you can do the recovery by using the Gelfand-Levitan, by using the so you can just do the recovery by using the Gelfand-Levitan theory. So if you know the complex valued pressure at the lips. But how about if you have only the absolute value? Well, then it turns out that you need to know the so-called discrete spectrum. You need to know some information about the bound states. Well, we notice that when we analyze the problem, so the lips play a crucial role. So the derivative of the vocal tract radius at the lips will be either positive or negative or zero. For example, when you say ooh, so the R prime of L is going to be zero. When you say oh, well, your upper lip is bent and the derivative will be negative. When you say ah, well, R prime of L will be positive. So it turns out that there are no bound states if R prime of L is positive or zero, but there's one bound state. So then you need to deal with that issue. So in the absence of bound states, then, well, you can use the Gelfand-Levitan theory and essentially get the result in a unique manner. And, so I will finish here. So here there are a few relevant references if you would like to do some reading. Well, so when I first started, I struggled because I couldn't understand the language of all these linguists. So I just came up with this summary for mathematicians, essentially. And so this is an article to deal, when you have the bound states, how you recover the potential from the absolute value of the Yost function. And well, this is a well-known book by Gunnar Funt, and so it's an excellent, so I learned a lot of things from this book. And there's also this famous linguist has an excellent book. And well, the Gelfand and Levitan, they had this famous paper, and there's also a well-known mathematician, and he has a book. Well, so muchas gracias, and I finish my talk here. If I went over, I'm very sorry.
Well, are there any questions? Yes?
Can you tell someone's age from the sounds they produce?
Yes. In fact, well, I didn't show this, but what happened was that there is this linguist named Brad Story. Well, he used the magnetic resonance imaging and collected data in 1994 and 2002. And let's see. So the solid line is the later one, and the dotted line is the earlier one. So I guess as people get older, somehow the vocal tract, so even though they produce the same sounds, but the formants change, I guess the shape of the vocal tract change, and perhaps you can just use this as an inverse problem. So, but at the same time, some people are able to, for example, they're able to control their muscles, and especially the movie actors, for example, that even though they are older, but they may sound younger. But they need to make an effort. But naturally, I guess as we get older, then things changed.
But how do they change? Is it the shape of the vocal tract, the vocal cords, or frequencies, or?
Well, I guess it depends on the individual. So, well, for example, here, if you look, for example, those formant frequencies change, and perhaps the amplitudes of those sounds change. So it depends on, I guess, the person. In fact, I'm taking care of an elderly professor. When he goes to the doctor, they say, "How tall are you?" And he says, "Oh, several years ago, I was 6'1", but now I'm 5'9". So I guess there are all these changes in our body, but it depends on how we take care of ourselves. And it depends on the individuals.
Thank you.
Well, question there.
Hi. You mentioned the implication of using this as a way to identify a person by the vocal tract. Now, it's clear to me that because if a person says one thing, let's say a sentence, let's say my mom goes to the market, and then asks another person to say exactly that same thing, well, then the change of the vocal tracts are actually kind of predictive or predictable, because you know what is the person is saying at each one of those points. But that's very language-based, and that's very actually what the person is saying. However, in the terms of if a person is talking in a completely unpredictable way, one person is saying one thing, another person is saying another, then the changes of the vocal tract are not that predictable. And so my question here is, how do you imagine that we can model that vocal tract in a way that it says, oh, that vocal tract is for that person, and that vocal tract is for that person, without assuming that they're saying exactly the same thing?
Well, you raise an excellent point. I guess mathematically, in fact, it's possible for example, somehow to control your muscles or your articulators, somehow to sound like somebody else. And the movie actors, for example, do this very well. But in the world, there's so many people, and well, they all speak in a different way. In fact, well, when I was a graduate student, this was many years ago, and one Turkish student came, and so I took him to the farmer's market. And well, he saw eggplants, and apparently he was just trying to buy them all. But then the farmer was saying, I was away, saying, "Continum, continum, continum." Well, he came and get me and asked me what the farmer was saying. But because he was Turkish, he couldn't understand. Well, it was impossible to understand the farmers unless you were there. So then I realized what was going on. The farmer was saying, "Are you counting them?" Because the farmer was selling the eggplants per item, not in per kilo. So I guess that besides the vocal tract, so in that case, you just need to have some additional measures to identify the person. In fact, that's why sometimes you don't use just one password, but there is some other, maybe you use a second password or...
Thank you.
Any other question? Well, I have a question. Now, somehow a technical question. To go to the infinite length, you extend it in a particular way, in a linear way, right?
Yeah, yes.
Doesn't matter how you extend it, or is...
Well, that's not the only way. So this is about extending the radius of the vocal tract in a linear way, whether you can do it in another way. Well, in fact, you can do it in an infinitely many different ways, but if you don't preserve the continuity of the radius and the derivative, well, you will be introducing some singularity or maybe a delta function. Then the mathematics will be a little bit more complicated.
But would the result be somehow independent in how we stand, or will it change a lot?
Well, what will happen is that you should not assign any physical interpretation of the extension of the vocal tract radius outside the mouth. In fact, this is still, I guess, a not settled area. So, namely, how the sound radiates beyond the lips. So, there are various theories. Well, for example, one theory is that you assume that you extend the sound is propagated, for example, in a cone of, expanding cross-sectional radius. Or the other is that now you have the point radiation, namely, your mouth is so small that now you have this half space, and the sound is propagated all over. So there are various theories. In fact, in the book by Funt, so they assume that the radiation occurs, but then it's not checked with the reality. Then they use the so-called a form factor. So they multiply. So when you hear the sound, so when you measure the sound frequency at a distance, to make up somehow the loss or the, so they multiply that by a factor, by a factor of frequency. They call it a form factor. Well, physicists and engineers always do this. So by using this, essentially they fix the errors.
And also there is the boundary condition at the glottis, the theta parameter. The boundary condition, the theta.
Yes.
How is that determined experimentally? How do they know what theta should be?
Oh, well, in this case, in my formulation, cotangent of theta turns out to be minus r prime of 0 divided by r of 0.
But how do you know it has to be that?
Oh, well, when I formulate the direct problem, so it turns out to be that way.
It has to be that. And this is constant, it doesn't change in time or...
Yes. Well, what happens is that the so-called regular solution defined in quantum mechanics, the regular solution evaluated at k equals 0 becomes r of x divided by r of 0 in the formulation. So let me see if I can find
Oh, there you have it.
Yes, so
Right.
it's right here. And then the boundary condition. This is very nice in the sense that normally you will not be able to go and make a measurement at the glottis. But this is sometimes called the inverse transmission problem. There is also the inverse reflection problem. In fact, some people propose the following. Well, if you measure, so you need to measure the reflection. So they were suggesting the following. Well, take a human being, push some air inside their mouth. And then that air will go through their throat and will be reflected. So you measure the reflection, and then you determine the shape of the vocal tract. But this is very uncomfortable. This would make, I guess, the person very uncomfortable. In fact, then some people were just using this on themselves. So.
Well, thank you. Well, okay. Well, last question, right? Oh, I mean, last two questions.
Well,
but here the drum changes in time. It's not the same drum, right?
Well, here you just assume that the shape of the vocal tract is fixed, and it produces a particular a pressure wave. But certainly, I guess in time, as we get older, the shape changes. Or in different environments, maybe depending on the room. So there may be many different physical factors that may be affecting the shape of the vocal tract. In fact, there are these ventriloques. Well, for example, they can just talk without moving their lips. So many things, I guess, can be done. So.
There's still a question there?
I was asking, you can model the vocal tract without knowing what the people is saying, right? You don't know which sentence.
Well, yes, because here I just measure the pressure wave. So it doesn't need to be a sound. But at the same time, if I use less data, well, for example, if I want to know what vowels are you uttering, so I only need to know practically the first two formants, F1 and F2. So it depends on how much information I have. So if I have less information, then I may not be able to determine whether the sound belongs to you. But if you utter, for example, some vowels, then with less information, I can just go to the vowel chart and I can see from your first formant and second formant what sound are you uttering.
And now, where do you have to take the measure? Just on the lips or inside?
Well, in my case, I can make the measurement at the lips because I'm using P of KL, so at X equals L. Or I can do the following. I can just assume that the vocal tract is a little longer, so I can make a measurement here, but then on this part outside, well, when I get the vocal tract from from X equals 0 to X equals L plus some large number, I can just ignore that part.
Okay, so it will be possible, just from recordings, that you can actually make the vocal tract, even if you don't know which was the length between the lips and the recording machine.
Yes. Well, by using the mathematical theory, so assuming that the propagation of the sound pressure in the vocal tract is governed by the Webster-Horn equation, which is a pretty good description, then this is the mathematics that I get. So I'm able to recover, if you give me the pressure measurement at the lips, then I can get the answer. In fact, it turns out that for large frequencies, I can just ignore because the frequency will go to a constant. In fact, I may be able to show you just one picture. So we used the vowel a from Brad's story, that linguist who used the MRI measurements. Well, he was using essentially the spectral theory. Basically, so these dots indicate his vocal tract area. So what we did was, so we used those dots and then got the pressure at the lips, so by using our theory. And then, well, here you see that the pressure somehow becomes almost a constant. And then we used this to recover the area, and the area given by the solid lines is what we obtained from these pressure measurements. Well, somehow, well, in this case, well, as you can tell, R prime, so this is A prime of L, that's positive, so there are no bound states in this case. But in case you have only one bound state, and if you know the shape of the upper lip during the utterance of the vowel, you can also use this procedure to get the vocal tract area in a unique manner.
Thank you. Any other question?
Yes, this is the frequency domain, the absolute value of the pressure.
Any other question? Let's say we are so late that they are still welcome now, right? Well, okay, otherwise we thank the speaker.
Muchas gracias.